Rotational motion is a little bit different than what we've looked at before. So far we've considered objects that could be modeled as a single particle, but now we want to take a look at extended objects like a wheel or some other shape that is spinning. So let's take a look at just such an object. Here we have a wheel, a gray wheel, and I've marked 4 places on the wheel with dots. We have a red, a green, a blue, and a purple dot. These could be little spots of paint on the wheel, for example. So let's actually start the wheel to rotating. So we can watch the wheel rotate, we can watch the motion of those individual places. After 2 complete revolutions, let's freeze the picture right here. And now let's take a look carefully at what's going on in terms of the velocity of each of those 4 locations. So let's focus on the red, the blue, and the purple spots. At the moment that we stopped the simulation, the red dot, the red particle, was going to the right. The blue particle was going straight down, and the purple particle was going straight to the left. So they were all going exactly the same speed, but notice that their velocities are in different directions. Even though all of these particles are part of the same rotating body, they all have different velocities, in this case because they're going in different directions. Now let's take a look at that green dot. That green dot was going exactly the same direction as the red dot, the red particle, but because it's closer to the axis, it's also not going as fast. So even though they have velocities in the same direction, they're going different speeds, which means they too have different velocities. And that's the challenge. If you have a rotating object like this wheel, every part of it is going to have a different velocity than every other part at any given moment, which means we can't simply assign one velocity to the object. The same would be true if we actually looked at the acceleration of each of these 4 particles. They would all be different. They would be in different directions, they would be different sizes, or both. And so that's the challenge for dealing with rotating bodies. The ideas we've been using, things like velocity and acceleration, are not very helpful because a different value applies to every part of the rotating body. So that means we're going to have to come up with a better way, a more appropriate way of describing a rotating body. So first of all, we're going to only pay attention to what's called rigid bodies. In other words, we're going to consider only objects that retain their shape as they spin. There are certainly objects that change shape as they spin. You could imagine a water balloon, for example. If you were to spin it around and around, it would actually distort and change shape as you spun it. That's a very complicated situation. But a great many objects, like wheels, for example, don't change shape noticeably as they spin, and so that's where the rigid body model comes in. So we're going to focus our attention on rigid bodies, objects that retain their shape as they spin. Now let's take a look at another rigid body as it spins. Here we have a rather unusual shape, and I've marked one location on the shape with a red dot so that we can follow it in particular. So I'm going to start this object to rotating. You can see it spinning around and around. Now what we're going to do is we're going to try to construct a motion diagram. So every 8 frames of this simulation, I'm now going to leave behind an image. So let's start doing that. And you can see that as the very oddly shaped blue object spins around and around, that one particular particle, that red dot, moves in a circle. Even though the object itself isn't round, the particle, the red dot, does move in a circle, and the circle is centered on the axis of rotation. So that's the first important observation to help us come up with a good way of describing rotational motion. And that is, anytime a rigid body rotates, every part of it is going to follow a circular path that's centered on the axis of rotation. So even though all the linear quantities are different for every part of a rotating rigid body, we saw, for example, that the velocity of every part of that rotating gray wheel was different at a given moment, we can still come up with some rotational or angular quantities, if you like, that are the same for every particle. That's our goal, to come up with quantities, rotational quantities, that are the same for every part of the rigid body. So we can assign a single value for each quantity that will describe the entire rotating rigid body. So again, remember that every part of a rotating rigid body follows a circle. If we go back and take a look at the animation of the wheel again, if I reset the simulation and start it in motion again, notice that every time the red particle goes all the way around, so does the green, the blue, and the purple particles. If the red particle goes all the way around its circle twice, all the other particles go around their circle twice. And so instead of talking about how far something moves, we want to start to talk about angles. Angles have to do with fractions of a circle, and every part of a rotating rigid body is going to rotate through the same angle, the same fraction of a circle at a given time. So when we go to describe rigid body rotation, the first thing we want is the position, or if you like, the orientation of the body, and that's going to be given by an angle. So if we define a radial line, a line from the axis of rotation to some particle on the object, then as that line rotates, it's going to sweep out an angle, and that angle is going to be characteristic of the entire rotating rigid body. Basically, that angle is going to define the orientation of the object at any given moment. Now, there are lots of ways to measure angles. You can certainly measure angles in degrees. That's probably the most familiar way. You could also simply count out revolutions or fractions of a revolution. That's the unit that we will be using in lab. In the next session, we'll be simply measuring angles in revolutions. Another angle unit that's common, in fact, it's the official one in science, is something called a radian. Now, we're not going to focus too much on radians, but it's probably useful to know where radians comes from so that we can talk about them from time to time, and you'll be familiar with what they mean. So if we want to understand what a radian is, here we have a particle, and the particle is going to be following a circular path around the plus, which is basically the center, the axis of rotation. As that particle rotates, we want to be able to define an angle. So suppose the particle starts out at the end of the dashed line to begin with, and as it rotates through an angle theta, the particle is literally going to travel a distance s. That blue line there is called the arc length. It's the distance traveled by the particle along its circular path as the line sweeps out an angle theta. Now, of course, for any circle, you can define a radius. The radius of the circle is the distance from the center to the edge. If you want to define that angle in radians, it's simply the ratio of those two distances. The angle in radians is the arc length traveled by a particle on the circle divided by the radius of the circle. And that's the reason it's the official unit in science. It's a ratio of two simple and meaningful distances. Now, if you think about a complete circle could be called one revolution. It's also 360 degrees. Think about the distance all the way around a circle. The angle in radians has to do with the arc length. If that particle moved all the way around the circle once, it would move a distance known as the circumference. And the circumference of a circle, you hopefully know, is 2 pi times the radius of the circle. So if the particle goes all the way around, s would be 2 pi times the radius. To get the angle in radians, you would then divide by the radius, and that would give you a total of 2 pi radians. So if you want a way to convert back and forth from different angular measures, one complete circle is one revolution, it's 360 degrees, or it's 2 pi radians. So now we have a way of describing the position or orientation, if you like, of a rigid body as it rotates. But now we want to go farther. We want to actually describe how it's moving. So think back to how we describe particles. The first thing we came up for describing particles was the velocity, which was how quickly its position was changing. We can do the exact same thing for rotating rigid bodies. We can define a rotational velocity, which has to do with how quickly its rotational position is changing. So you take the change of angle, if you will, as it rotates, you divide by how long that takes, and that would be what's called the rotational velocity. So this is the traditional symbolic way of representing that. So we have delta theta in the numerator. That's the change of position, the change of angular or rotational position. Delta t in the denominator, that's the time. The funny looking symbol out front is actually a lowercase Greek letter omega. That's the traditional symbol for rotational velocity. So we have lots of units we could use. Depending on what unit you use for measuring the rotational position and for measuring the time, we could have revolutions per second. That's the unit we'll use in the next lab. You could have RPM, revolutions per minute, degrees per second. In red there is radians per second. That would be the official unit. But in fact, any of these are perfectly fine. Now remember, velocity though is not just a number, it's a vector. There is not just how fast something is going, but the direction it's moving. In the case of rotating rigid bodies, we have to talk about the direction the object is rotating. And there are a variety of ways to do that. The most familiar, and the one that we'll use typically, is just to use clockwise and counterclockwise. As long as you can agree on how to look at the object, clockwise and counterclockwise are excellent ways of indicating the direction of rotation. But be careful, just like right and left are relative directions. Which direction is right and which direction is left depends on which way you're facing. The same is true for clockwise and counterclockwise. If you look at something and describe it as being clockwise or counterclockwise, if you were to turn around and look at the same object, you would come up with the opposite answer. So just like left and right are relative directions, so are clockwise and counterclockwise. So just be careful about that. Now, velocity alone was not enough to describe a particle. Remember, that was one important ingredient. The other ingredient was the acceleration, which told us how quickly the velocity was changing. We can do the same thing for rotational motion. How quickly the rotational velocity is changing is going to be called the rotational acceleration. So we'll take the change in the rotational velocity and divide by the time. So we have delta omega in the numerator. That's the change of rotational velocity. Delta t, that's your change of time. The funny symbol out front, that sort of fish-looking symbol, that's a lowercase Greek letter alpha. That's the traditional symbol for rotational acceleration. Again, there are lots of possible units. We'll be using revolutions per second squared in the next lab. Other units are fine though. The official one again would be radians per second squared. Just like the rotational velocity has a direction, so does the rotational acceleration. It too, for a fixed axis of rotation, can either be clockwise or counterclockwise. And if you look carefully at how we've defined these are defined in exactly the same way we did for the particle case. For particles, the velocity was how quickly the position was changing. The acceleration had to do with how quickly the velocity was changing. These are defined exactly the same way for the rotational case, which means they can be interpreted in the same way as well. Remember, for a particle, if it was speeding up, the velocity and the acceleration were in the same direction, and if it was slowing down, they were opposite. The same applies to the rotational case. If something is rotating and speeding up as it rotates, that means its rotational acceleration will be in the same direction as its rotational velocity. They'll both be clockwise or they'll both be counterclockwise. And if something is slowing down as it spins, then they will be in opposite directions. If one is clockwise, the other will be counterclockwise. So we've carefully defined these things so that they're very much like the quantities we came up with before. So between the rotational velocity and the rotational acceleration then, we can completely describe how a rigid body is rotating. These two together are unique to the rotating body. They apply to all of it, and they completely describe how it's moving. Now, if we go back one more time to look at the rotating gray wheel with the colored dots, let me set it into motion one last time. The whole point of coming up with rotational velocity and rotational acceleration was that we could assign one value for each to the entire rotating body, and that would then completely describe it. And that's good, but there are still times when you'd like to talk about the linear quantities, the linear velocity or the linear acceleration that applies to a particular particle that makes up that rigid body. So for example, maybe we wanted to know exactly how fast the green particle was moving as the entire wheel rotated. In that case, we need a way to convert back. Knowing the rotational quantities, how do we work backwards and find the linear quantities that describe a particular part of the rotating body? In the case of the velocity, which is usually the one that's of interest, here's how we do it. The linear speed of any particle that makes up a rotating rigid body can be found by taking the rotational speed and multiplying by how far that particle is from the axis. If you like, we can write it like that. V is equal to omega r. So again, omega describes the entire rotating body. Every part of a rotating rigid body has the same value of omega. But if we want to know how fast the actual speed of a particle on the rigid body, part of the rigid body, as it's spinning, and how fast it travels along its circular path, this is how we do that. We take the rotational speed and we multiply by the distance from the axis.